today's problem from linear programming problem, and basically it is from simplex method of LPP, and the problem is find x1, x2, x3 greater or equal to 0 subject to these two conditions are given, these two subject to or constraint are given, and which will maximize z. This is equal to 10x1 plus x2 plus 2x3. This is the objective function, and the first condition is the variable, and we say it the non-negative restriction of the LPP. Okay, and in the second part of this problem, it is also says that satisfy yourself the matrix written in each table in place of the initial basis matrix gives the inverse of the basis of the iteration. Okay, we clear the meaning of the second portion after solving the solution or after solving the problem by simplex method. To use simplex method, it is clear that we have to introduce two slack variable here. In the first constant there be one slack variable, and in the second constant there be another one slack variable. So we introduce two slack variable x4 and x5 in the first and second constant, and the problem can be rewrite as, we write first the objective function, which is max z. This is equal to 10 x1 plus x2 plus 2 x3 plus 0 x4 plus 0 x5. Okay, the coefficient of slack variable are 0 in the objective function, and the constraints are subject to x1 plus x2 minus 2x3 plus x4 plus 0 x5. This is equal to 10, and the second constant is 4x1 plus x2 minus x3 plus 0 x4 plus x5. This is equal to 20 with xj greater or equal to 0 for j. This is equal to 1, 2, 3, 4, 5. Okay, this is the standard form of LPP. Now we draw the first simplex table of this problem. First fill the first simplex table from the given problem. We first fill the row of Cj, that is the row of cost vector, which is given by 10, 1, 2, 0, 0. This is 10, 1, 2, 0, 0. This is the cost vector, right? And now we write the matrix, that is the main matrix of the problem. This is 1, 4, 1, 1, minus 2, 1. This is given by here 1, 4. This is 1, 1. This is minus 2, 1. This is 1, 0, and this is 0, 1. Clearly 1, 0 and 0, 1, these are two standard bases. So in the basis there must be a4 and a5, these two vectors. So we write here the basis vector a4 and a5, and the corresponding variable are x4 and x5 obviously, and we write the column of B. This is given by 10 and 20, 10 and 20. Okay, now the cost corresponding to a4 and a5 are given by a4 and a5 are 0, 0, 0, 0. Now we calculate the net evaluation Zj minus Cj. What are Zj minus Cj? Zj minus Cj is 0 into 1 plus 0 into 4 minus 10. This is minus 10, and this is obviously minus 1, this is obviously minus 2, this is 0, this is 0. And the most negative appears corresponding to the column A1. So it is clear that the vector A1 is incoming vector, or it introduced in the basis. And how to find the outgoing vector? To find the outgoing vector, we have to calculate the mean ratio. How to calculate mean ratio? 10 by 1. This is the first mean ratio, and second mean ratio is 20 by 4. So this is 5 and this is 10. Obviously this is minimum. We write here minimum. So this row is the key row and this is the key column. And intersecting element of key row and key column is the key element. Okay. And since in the key row there be the vector a5, so a5 must be outgoing vector. Okay. So we introduce a1 in the basis and automatically a5 is out of the basis. Okay. Now to go to the second simplex table. In the second simplex table, we first fill the basis vector column, that is the column of B. What are the column of B? The column of B is A4. This is unchanged as the previous table, and we write A1 in place of A5, right? A1 in place of A5, and corresponding variable are X4 and X1, and the cost corresponding to this vector A4, this is 0, and A1, this is 10. This is 0, this is 10. Now to make the key element into 1, we make the operation as we write here in the column of operation R2 dash, this is equal to 14 into R2, and this operation is made on all the element of this row, and the transferred row becomes, or new row becomes 20 by 4, this is given by 5, 4 by 4, this is given by 1, this is 1 by 4, this is also 1 by 4, this is 0, and this is also 1 by 4. Now to make it 0, we here made the operation R1 dash, this is R1 minus R2 dash. Okay, because new R2 is here 1 and old R1 is 1, so this is 0. Now it becomes 10 minus 5, this is 5, and this is 1 minus 1 by 4, this is 3 by 4, and this element is given by minus 2 minus 1 by 4, so this is minus 9 by 4. Clear? And this is 1 minus 0, this is obviously 1, and this element is minus 1 by 4. Now we calculate all the net evaluation. Clearly this net evaluation is 0, and this is 10 into 1 by 4, that is 5 by 2 minus 1, so this is given by 3 by 2. Clear? And this is 10 into 1 by 4, this is 5 by 2 minus 1 by 2, this is given by 5 minus 4 by 2, this is half, and this is given by 5 by 2 minus 0, and this is obviously 0 because this and this are bases. Okay, and it is clear that all the net evaluation Zj minus Cj get equal to 0. So we write here, since Zj minus Cj get equal to 0 for all j, so condition of optimality satisfied. And we write from this table the optimal solution of the problem, and the optimal solution is given by x1, this is equal to 5, x2, this is equal to 0 because there is no x2, and x3, this is also equal to 0. Okay, since there be no x3. And we cannot write x4, the value of x4 is 5 because x4 is not the original variable, this is slack variable. Okay, and now fill this cell, and this cell is given by 0 into 5 plus 10 into 5, this is 50. So with z max, that is the maximum value of z, we want to find the maximum value of z, this is given by 50. Okay, this is the solution of the problem by Simplex method. Now we understand the second portion of this problem. Satisfy yourself that the matrix written in each W in place of the initial basis matrix. Here the initial basis matrix are A4 and A5. Okay. Here we see the column of A4 and A5. A4 and A5. And we write here the column of A4 and A5. This is A4 and this is A5. We write this 1, 0. This is minus 1 by 4. This is 1 by 4. And we write it in the form of a matrix. Okay. And here the basis is X4 and A4 and A1. We write the value of A4 and A1 here. A4 is given by this and A1 is given by this. We write A4, A1. This is 1, 0 and 1, 4. Okay. Now here we write A4 and A5. Okay. We write these two columns and here we write A4 and A1, these two columns. If we name this matrix as the matrix A, it is very easily seen that this is nothing but A inverse. Okay. And this verification is needed for the second portion, because here we get the matrix A from the basis of the second column, second table, and this inverse is given by A inverse. It is in the second table, which are in the basis of the first table. Okay. So we verify the condition. Okay. So these are the complete solution of the problem. Thank you for watching.